Good morning, everyone. My name is Mahmoud Zanaki, and I am pleased to present our work on effective models for hard scheduling and transportation problems. This research was conducted at the University of Science and Technology of Iran, Mohammed Boudiaf, within the Simple board. Our presentation is structured as follows. I will start by introducing the problem and its significance. Then we present a model inspired by the vehicle routing problem to optimize the shuttle bus scheduling in Arafat region. We'll propose after that an algorithm and a bottleneck model to efficiently assign pilgrims to different areas in Arafat while minimizing congestion. We'll showcase experimental results demonstrating the effectiveness of our models. Finally, we will summarize our findings and discuss possible future improvement. Each year, Hajj leads to significant road congestion, causing delays in transportation and frustration among pilgrims due to limited space availability. To facilitate movement between the holy sites, several transportation options are provided, including pedestrian pathways, regular buses restricted to a single trip, shuttle buses, and a Mashair train. Based on their nationality, pilgrims are split into zones, also known as establishment, such as Southeast Asia, South Asia, non-Arab African, Arab countries, etc. Each establishment has its camp, routes, and parking spaces to handle the movement of pilgrims. Recent studies have focused on optimizing the scheduling of pilgrim transportation to minimize travel time. However, these approaches vary in terms of spatial and temporal constraint, as well as the optimization techniques employed. Mathematical modeling is the most used. It has the advantage of being formal and allows direct use of mathematical solvers. Meta-heuristic based on stochastic processes such as genetic algorithms are also used since ILP modeling is NP-complete. However, mathematical modeling requires precise definition of objective. In this study, we specifically focus on Arafat Day. We develop efficient mathematical models to optimize the scheduling of pilgrims during this crucial period. These models surpass those in existing literature by offering more precise solutions while ensuring reduced CPU computation time. Building upon the discussed optimization approaches, we present a graph-based model specifically designed to enhance the efficiency of pilgrim transportation. Whether we consider the route Mecca-Mina-Arafat or Arafat-Muzdalifa-Mina, we can model the transport of pilgrims with shuttle buses by a graph where a node represents a bus stop and an arc represents a section of road connecting two nodes. At each site there are bus stops. These stops can be either departure, arrival, or intermediate nodes. To formulate a model for this problem, we introduce the following sets: a set of start offices, a set of end offices, and a set of office stops, intermediate nodes. We have also the set I, where pilgrims are waiting, and the set G. We define the set of available shuttle buses L. The goal is to determine a set of optimal routes between start offices and end offices, ensuring passage through intermediate bus stops. We consider in the proposed model the following decision variables: X, I, G, L, binary decision variables equal to 1 if bus L goes from node I to node G, and Y, I, L, integer decision variable representing the number of pilgrims picked up in node E by bus L. Here is our mathematical model that formalizes this problem and optimizes the pilgrim transportation routes. The objective function 1 represents the overall travel time to be minimized. The objective function includes three terms. The first represents the overall travel time between start nodes and intermediate nodes. The second term represents the overall travel time between intermediate nodes, and the third term, the overall travel time between intermediate nodes and end nodes. Constraint 2 and 3 indicate that each intermediate node must be visited by at least one bus. Constraint 4, 5, and 6 represent the flow constraints that ensure that each shuttle bus starts from a start node, then visit at least one intermediate node to finally go to an end node. Constraint 7 eliminates infeasible solution which contain subtowers in intermediate nodes. This constraint, called MTZ constraint, was introduced by Miller and al. For travel salesman problem and use continuous variable U used to eliminate subtowers in intermediate node sets. Constraint 8 prevents a shuttle bus from starting several times. Constraint 9 indicate that the shuttle bus's capacities must not be exceeded, while constraint 10 guarantee that all pilgrims will be picked up by the shuttle buses. Finally, constraint 11 and 12 keep the model coherence between decision variables x and y. Even if the models seem complex, but we can easily solve medium-sized instances with a mathematical solver. Indeed, for an establishment using 100 shuttle buses with a transport network composed of 50 nodes, the proposed model has approximately 50,000 variables and 4,200 constraints that can be solved optimally in a reasonable time. The proposed model is an integer linear program, and for large instances, it can be solved with both mathematical solver and meta-heuristics. The solver can provide bounds as well as feasible solutions. These can guide the stochastic search process toward higher quality solutions and speed up the search process. We now turn our attention to another model designed for the optimal location of pilgrims in the Arafat region. We present an algorithm alongside a bottleneck model to address the assignment of pilgrim groups to various zones in Arafat. This allocation is based on the arrival times while considering capacity limitation. Our approach enhances the organization of the Arafat plain by reducing spatio-temporal congestion in infrastructure usage. We have a set R of resources areas of Arafat of capacity Q, and a set of groups of pilgrims arriving at time T called G, of size N. UR represent aggregated capacity utilization for resource R. In our model, the decision variables are XGR, corresponding to number of pilgrims of group G assigned to resource R, and U, a bottleneck decision variable representing maximum of capacity utilization to minimize. The proposed model is a min-max or bottleneck program in which we try to minimize the maximum aggregated capacity utilization over all considered resources, as depicted in this figure. This allows a balance in the distribution of pilgrims in Arafat. We present now the bottleneck model and the algorithm used to solve repeatedly this model. Constraint 2 is used to calculate the maximum utilization of all resources. Capacity constraint 3 and 4 are used to calculate aggregated utilization levels of the resources. The objective is to determine lowest possible capacity utilization levels given the current pilgrim numbers and their spatio-temporal distribution in Arafat. As described in the algorithm, we accomplish this by repeatedly solving problem P at each arrival of pilgrim groups and updating parameters UR. Saturated resources are moved from the model, line 6 and 7 of the algorithm. The assignment process continues until the area of the considered establishment becomes saturated or no pilgrims arrive, line 2 of the algorithm. However, when resources have different capacities, resources with low capacity become full before other resources, causing a spatio-temporal peak in these low capacity resources, while others still have free space. We can improve the model by considering bottleneck on densities rather than on available space in resources. We propose to change constraint 2 as follows. Experiment carried out for large instances showed that the bottleneck model ensures a balanced distribution of pilgrims over the considered region of Arafat. To evaluate the effectiveness of our proposed mathematical models, we now present the results of our experimental simulations. The models are solved with Cplex on a workstation Xeon, and all algorithms are implemented using Python language. The following table summarizes the experimentation realized on pilgrim transportation model. Medium-sized instances were randomly generated ranging from a graph of 60 nodes and a fleet of 40 shuttle buses to 100 nodes and 50 shuttle buses, which correspond to instances of one establishment in Hajj. We give for each instance the obtained solution value, optimal or near optimal, and the gap with the lower bound in case of approximate solution. The problem size is represented with the total number of graph nodes n, that is n equal s plus b plus e, and the shuttle bus fleet size m. The buses have the same capacity of 60 pilgrims. The distances between nodes were generated randomly in the range 100. The optimal solution has been reached in 3 instances, 3, 4, and 5. But if we consider that the gap less than 5% corresponds to a near optimal solution, the obtained results are encouraging, since the lower bound in models with binary variables is generally quite far from the optimal solution. However, a gap greater than 10%, instance 1, doesn't provide information on the quality of the obtained solution. A meta-heuristic approach can lead to better results. We move on to the experiments regarding the pilgrim assignment problem in the Arafat zone. The main goal is to test the ability of our approach to balance the distribution of pilgrims in Arafat region. We consider that the region of Arafat dedicated to a given establishment is divided into 10 areas with a total capacity of 32,385 pilgrims. The estimated capacity in number of pilgrims for each area is as follows. Gradually, a group of pilgrims arrive at Arafat. We consider an arrival of 1,751 pilgrims divided into 9 groups. After solving the bottleneck program P, the pilgrims are distributed over the 10 zones in a balanced way as follows. The maximum density is 5.42 at areas 4, 8, and 10, with a gap of 0.01 with the optimal density equal to 5.41%. Other groups of pilgrims will arrive at different times, and our algorithm, along with the bottleneck model, will ensure a balanced allocation. In this table, we summarize the experimentations realized on large instances. We give for each instance the solution gap and average CPU time for solving one bottleneck program. The instance size is represented with the number of Arafat areas, the total number of arriving pilgrims, and number of time arrivals. The model size is depicted with the amount of integer variables of program P. We can notice that even for large instances, the bottleneck model size remains acceptable. It takes a reasonable CPU time to solve. The results are very encouraging. The bottleneck program ensures a balanced distribution of pilgrims over the considered region. We now move to the conclusion, where we summarize our key contribution and discuss potential future directions. This work has proposed mathematical model for transportation and scheduling pilgrim in Hajj. A VRP-based model is used for the pilgrim transportation by shuttle buses from Mina to Arafat and from Arafat to Muzdalifah. We show that realistic instances can be represented by this model. The pilgrim scheduling problem in Arafat zone has been solved by an iterative algorithm which solves a bottleneck problem at each iteration. Cplex solver has been successfully used to solve realistic instances, and high-quality solutions were obtained in reduced CPU time. As future perspective, we plan to use meteoristics to solve large-scale instances. Thank you for your attention. I'm happy to answer any questions you may have.